Hello world, this is Craig. In the last video we talked about how to program this 8155 timer and how to start it and the different modes of operation. In this one, let's finish up the timer part of this by talking about how we read back the counter to find out how many ticks are left in the current count until it reaches the terminal count. Okay, so let's talk about reading this counter back in. So in the last time we talked that we write an output to the port register that goes into the initial count register when we do the run, and then for each count that value gets transferred into the working count register, and when we do a read of the working count register using the in instruction, we get the value of that count register, and that's going to be a 14-bit value coming in just like it was when we pushed it out. Now in the Intel literature they say their stated goal of this counter was for it to be able to make a square wave. Okay, the little one-shot mode was kind of a secondary. Their primary drive was to get this to operate as a square wave. And if you have it in continuous mode, of course, this just makes a continuous square wave. So we can all think of different ways that we would have made a counter or in software to create a square wave. For example, we could have taken the initial count, simply done a rotate to the right by 1, and that would divide it into 2. And then we could have just counted that down once and then reloaded it and counted it down again. That would have been a simple way to do this. Intel, for some reason, chose a quite a bit more complicated way. And let's talk about how they actually did this. And the reason it's important to know how this counter works is if you want to read these numbers back and get any understanding of what number you're getting, you have to understand how this counter works. First of all, Intel does do a little description of what this counter actually does. They say that if you load an even count, so let's say that we're going to load 8, in the first step we load the 8, and then for every tick of the timer after that it decrements it by 2. So it's going to go 8, 6, 4, 2 till it gets down to 0, and when it gets down to 0 it's going to reload that again. You're going to have 8, 6, 4, 2, 0, and then to get back to where we were to begin with, we got to reload our 8. Okay, but if we count up how many of these there actually are, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when we loaded a value of 8, it takes 10 ticks to get back to where we started from. There's something wrong with their description. Now, if we do an odd value, this is what their description is. So let's say that if we loaded 9, we do an odd value, we're going to get a 9, we're going to start with a 9, and then we're going to, in the first tick, we're going to subtract 1. So we're going to go from 9 to 8 in the first tick. And then we're going to count down by 2. So we're going to go 6, 4, 2, 0. We're going to then reload our 9. But they say in the first tick after this reload, it subtracts 3. Where up here, it subtracted 1, and all these others it subtracted 2. Here they say it's going to subtract 3. So now we're down immediately to 6, 4, 2, 0, and to get back to where we were, we have to load the 9 again. So that took 11. So again, we have 2 more extras than we had before. And we could just say, well, maybe there's something here that gets missed, so we don't actually count the one that begins with. But at any rate, if we believe the explanation they give for how these counters work, and when it comes back that we're going to read these counts, we'll never get the right answer. We'll never get how many counts are actually there. So let's look at how this has to work in order to get the right values. Okay, so piecing together from the spec sheets, this is what we know. What we know is we've got a 14-bit counter, and we know that they take the least significant bit and they use that for a flag. They use that for a flag because they're going to decrement this counter by 2 so that they can get the square wave. What that flag tells us is if we're in the first half of the count or in the second half of the count. So here that flag is going to be equal to 1. Here that flag is equal to 0. Here the flag's 1. Flag 0 again. And so we can see that this flag of the least significant bit is actually the same value as the output pin. So if that flag is 1, our output pin is 1 for the timer output. And if that flag is 0, then our output pin goes to 0. So that flag we can see already, they could just be sending that bit, that least significant bit, out as the pin for the timer out. Okay, so that's one thing that we know from the spec sheet is they're using that least significant bit as the flag. And also that least significant bit represents the output pin. Okay, so now let's look at if we do an even count, what has to be happening for this to work. So we have our initial count, and if we're going to do an even count, let's say in this example we're going to do 8. When this goes from the initial count into the counter, they add 1 to it. So we take our initial count plus 1 to set that flag. So you can say that they're just setting that flag to 1, or you can say that they're actually incrementing that count in order to set that flag. Because it was even, that bit was originally 0. Now we're going to set that to 1. We can either say that we incremented it by 1, or we just manually, physically set that flag to 1. But at any rate, the result is that the value that's in the counter is 1 more than what our initial count was. Okay, and so that's going to look like a 1001 after we have added our additional number to it. Okay, so that's 9. Now this will go and it will decrement by 2. So it'll go 9, 7, 5, 3, and that's just what they, 9, 7, 5, I got one extra one in there, 3, so decrementing by 2. So let's look at this 3, that's 0, 0, 1, 1. 5 was 0, 1, 0, 1. 3 is actually the terminal count. So as it turns out, they have to, at 3, stop and reload the value. But this time when they reload, they don't add 1 to it, because now we want the least significant bit to be 0. Since this was an even number, the least significant bit was already 0. So now they just take whatever was in the initial count and they reload that back into the counter as 1, 0, 0, 0, which was our 8 again. Now we just decrement by 2. So 8, 6, 4, 2. Now when we get down to 0, 0, 1, 0, which is 2, this is our terminal count. When we get to our terminal count of 2, now we reload our value, our initial count, plus 1 again, and we're back up to the 9. Okay, so if we look, we get 1, 2, 3, 4, 5, 6, 7, 8. So this is the correct number of pulses. This is 8 pulses that it took to get from where we started with 8 in the counter to where we ended with 8 in the counter. Okay, so when we're reading our values back, this is the way that we need to understand that the counter works in order to be able to interpret these values. Okay, now let's load an odd value and see what happens. So let's load 1001, which is 9 in decimal. Okay, we load this. The least significant bit is already a 1, so we don't have to add 1 to it. We simply take the initial count and we go into the counter as 1001, which is 9. But now, rather than decrement by 2 like we did if it's an even value, we don't do anything the first tick. So the first tick, we subtract 0, and so we still have 1001. So we still have got 9, where we had 9 before, we have 9 now. Now what we do is we go into the mode where we're subtracting 2 again. So we'll go 9, 7, 5. We get down to 3 again, which is our 0, 0, 1, 1, and this is our terminal count. So you can see that our terminal count is all zeros and then a 1, and we don't care what it is. It's either a 1, 1 or it's a 1, 0. But in either case, those are our terminal counts when we're going to reload. So now that we're halfway through, our initial count was 9. Our initial count was 9. We're going to take our initial count minus 1 and load that into here, which is 8. Then we're going to decrement by 2, just like we did before. 6, 4, 2. So now we're down to 0, 0, 1, 0. This is our terminal count again. When we reach our terminal count, we're going to go back and reload our initial count, which is odd. The flag is already set, so we just reload the initial count as it was. Okay, and that's back to 9. Count these up. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have the 9 pulses promised in order to get back to where we were again in this loop. So this is the way that the counter actually seems to be working if we load if we load an even value, the first time it loads the initial count plus 1, and then it counts down by 2s until it gets to a terminal count of 3. And then we're halfway through, so we need to set that flag to 0. We reload the value. It's already set to 0. We count down by 2s until we get to our new terminal count, which is 2 in decimal. And then we reload the value just like we did before, plus 1, and we get back to 9. So this is how it works if it's even. That's how it works if it's odd. So how do we take that information and actually get the count back out of it? Let's save this for a second. So the way to understand what value we're getting out of the counter, we need to think of this counter as being 2 halves. Okay, so this is what we're going to call the first half, and this is going to be the second half of the count. Okay, so the first thing we do is we get the count, and we then look at the flag. If the least significant bit is equal to 0, then we're done. We don't have to worry about it because the least significant bit being 0 means we're in the second half of the count. So we just take our count. If the least significant bit is 0, all we have to do is take our count and divide it by 2. Because, remember, we're counting down by 2s, and so we have to take our count and divide it by 2. And then this is the actual number of ticks left. Okay, so it's pretty simple. If we're in the second half, it's pretty simple. But now, if we redo 2 with the least significant bit is equal to 1, now we have to do the same thing. We will take what the count actually is, all 14 bits. We will divide that by 2, and we'll divide it by 2 by rotating once to the right. And we will get a value that tells us how many ticks are left in this half of the count, but this time this half of the count is the first half of the count. Okay, so either time we're finding out how many ticks are left in the current half of the count. It's just whether we're in the first half of the count or whether we're in the second half of the count. So least significant bit is equal to 1. That means we're in the first half of the count. We do the same thing till we find out the number of ticks left in this half. Okay, but then what we have to do is we have to take the initial count, we have to divide that by 2, and we have to add that to the number of ticks that were left in this half, because the initial count divided by 2, that's the number of ticks in the other half. So, for example, let's say that we read 5, which is 0101. That's how many ticks are in our half. So what we're going to do is we're going to rotate this once to the right into the carry. Okay, so this is going to go into the carry, and the actual number of ticks we're going to get left is this rotated to the right, so that 1 is gone, so we're going to get 010. That's how many ticks are left, which is 2 in decimal. Since this was 1, we have to take half of our initial count. And let's say in this example, our initial count was either 8 or 9. It doesn't matter. If our initial count was either 8 or 9, half of our initial count would have been 4. So the total number of ticks left is 2 in this count, 2 in this half, plus 4 from the other half. So there's a total of 6 ticks left. Okay, now let's say that we did that same example, but instead of getting a 5, we read back a 4. So that's a 0100. Now we move this into the carry. We do a rotate right. We move that into the carry. This tells us the same thing it told us before. There are 2 ticks left in this current half. Okay, so there's 2 ticks left now. But this is 0. So there's 0 ticks left in the other half. And so 2 plus 0 says there's 2 ticks left in the total cycle. Now, the reason it didn't matter if we had 8 or 9, because if there's an odd value, remember the extra tick showed up in the first half. So whether we have an initial count of 8 or 9, there's going to be the even number, or 4 ticks left in the second half. So when we do this, the easiest way to do it is just take the initial count and rotate right and throw the least significant bit away, because it doesn't matter what that least significant bit was, that least significant bit would have shown up as the extra tick in the first half. So let's actually do examples. And remember, this is a 14-bit value, but we are just doing the example when we get down to a value of 8 or 9 to begin with. But this would work no matter what that value was to begin with. Let's say their initial value is going to be 8, and we do the first clock pulse. It loads that output register into the initial count. Remember, I said that if we're doing a repeating cycle, the first cycle has got one more tick in it than the others because this clock pulse first moves that tick over into from the registers into the initial count. Okay, so now we have it in the initial count. We're ready to do our repeating little loop. First thing we do is we take our initial count, add 1 to it, and put it into our counter. So we would have 9. And we can see this column shows us what the value is, but it's split here. So we can see the flag is a 1. And then this is the actual number of ticks left in this half, so that 9 is the same as having a 4, and then 1 times the number of ticks in the other half is a total number of 8. So if we first load this counter and we immediately do a read of it, it'll tell us that there's 8 ticks left before this is completely done with its cycle, which is correct because we loaded 8. We can see we go on down. Let's do another example. We do tick tick, so we decrement 2, we're down to 5. 5 is 0, 1, 0, 1. We look at the flag is still 1, same kind of thing. This is the example we did earlier. We have 2 ticks left in this half. We have 4 ticks left in the other half for a total of 6. We get on down to where we have done 2 more ticks. We see the terminal count at 3. Cause us to do a reload. We reload the initial count just as it was because the flag is already set. That's an 8. And so you can see right now if we did a read, we would get a 4 in this half, but 0 times however many were in the other half, and so there's 0, and so our total number is 4, and that's correct. Right after we do that reload, it'll tell us that we have 4 ticks left, which is true. We do another tick. We say decrement 2, decrement 2, decrement 2. We're now down to 2, which is 1, 0. That's our terminal count that's going to cause us to reload. It tells us that there's 1 tick left in this half, 0 ticks left in the other half for a total tick of 1. That tick comes along. The output now goes high because we've moved the initial count plus 1 into the counter. That least significant bit is now a 1 because that's the flag. It tells us we're back into the first half. And again, we have a count of 4 in this half, 1 in the other half for a total of 8 ticks left. And the output has gone high. And we're to the point where we can just repeat that. Okay, so this is what it looks like. If we loaded a count of 8, this is what it would look like as we counted through. And we can see that it repeats in the correct time at 8. And every time we do a request, we will get the correct value. Now let's look if we load an odd value. So again, when we do the run, it moves it from the register into the initial count register. And so that's that extra one that shows up at the beginning. The initial count moves into our counter. So we get 9 into the counter. And we can see we've got 4 in this, 4 in the other for a total of 8. The first tick, we don't decrement at all. So we still have a 9. Okay, so we still have 4 in this one, 8. So notice this is one more little quirk in the timer, and that is that if we load an odd count, we have to wait until we're 3 counts into it before we get the right value. Okay, so we don't have that problem when we loaded an even number. It's only when we load an odd value. We have to wait until at least the 3rd tick before we get the right value, because you can see this time we would have gotten the answer of 8 in either the first tick or the second tick. And we wouldn't know if we just read it. We wouldn't know if we were in the first tick or the second tick, but we have to wait until the 3rd one before we know if we've got a good value. Okay, we go on down a couple more ticks. Decrement 2, we're at 5. Just like we got before, there's 2 in this half, 4 in the other half for a total of 6. Decrement on down until we reach the first terminal count of 0011. When we reach that, the flag is set to 0 because we're now going to load an initial count minus 1. So we're loading 8. Flag goes to 0, so the output pin falls. Now if we did an immediate read, we would see that we got 4 ticks left in this half, 0 in the other half because the other half is already done for a total of 4. Tick, tick, tick. Now we're down to 2, which is the new terminal count. We've got 1 in this one, 0 in the other half for a total of 1. That one more tick goes away. We reload the count and we're back to where we started from. Okay, so these are the values that we would get if we actually read this every time with every tick with either an even or with an odd value. So let's expand a little bit on this and actually do the full procedures that you need to do in order to get a count. Well, the zero thing you have to do to get a count is you have to stop the counter. You got to stop the counter if you want an accurate value of this number of ticks left. Now, the 3-channel version of this, you don't have to stop the counter, but in the 8155 you do. So the first thing you need to do is stop the counter. Okay, then you get the count, and by getting the count, we're going to do an N of the high byte, and let's say we're going to put that into one of the register pairs. So let's put that into the B. So we're going to do an N of, in this case, it's going to be 4 or A4. So do an N of either of those registers. Remember, this is if you're using version 1 of the hardware, version 2 of the hardware. You do an N, let's put that in C, that's our lower register, and then let's do another N of the 4 or 5 or the A5, and let's put that in the upper register. So now we have BC, which is our number of ticks left in this half in our BC register pair. We do a register rotate, so we do a rotate once of that register pair, and that gives us a divide by 2, and it will take this flag and put it into the carry. Okay, if the carry is 0, we're done. We've already taken into account our divide by 2, and we know that there's no ticks left in the other half, so if the carry is equal to 0, we're done. We've got our number of ticks. Actually, what we want to do before that is we want to clear the top 3 bits, because we don't know what those top 3 bits are. They were when we read back in the mode, which we didn't want, and then this bit after we did the rotate, depending on which rotate we did, that could be a 0 or it could be something that we didn't know what it is. So we do want to clear the top 3 bits before we call this done. All right, now if we read those 2 registers in, but we found that our carry was set, so our least significant bit had been 1, we do the exact same thing. We rotate that right, we clear the top 3 bits, so now we know how many ticks were left in this half, but now we have to take the initial count and let's put that into the, say, the DE pair. Let's load our initial count into the DE pair. We then do a rotate 1 to the right to divide by 2. Then we just add those 2 together, and presumably the top 3 bits in our initial count were already equal to 0, so we didn't have to clear those. That's how we read the number of counts that are left. So the first thing we do is we stop the counter, and we do that by writing a 01 to the command register. We input the low byte and the high byte of the count into some register pair. We rotate right into the carry. We clear the top 3 bits. We look at the carry. If the carry was equal to 0, we're done. If the carry was equal to 1, we've now got to go get the initial count into a register pair. Because we're counting by 2s, we have to divide that by 2, and we do that just by rotating once to the right. And then we add those 2 numbers that we have, the number that we got from reading the registers and the number we got from the initial count, and then we're done. Of course, the 8085 doesn't have register pair rotate, so in doing these things it takes 3 or 4 more instructions for each of those to do the rotate with the double registers, but still it's not that big of a deal. Okay, one more thing to add about reading the timer. Since we stopped the timer here, there isn't a command using the register that we can using the command register, that we can just restart this timer again based on the value that it already has. If we give this a run command using the command register, it's going to reload the value that we originally output to this port register. So it'll reload that and use that as the new initial count. And if we were done with that count, if we just wanted to read what it was and we were done with it, we want to start over again, that's fine. It'll just take whatever value we had and whatever mode we had, and it'll reload it. But if we wanted to continue counting, we have to take the values that we got when we did the in instruction, and we have to feed those back out to the port with an out instruction. So to back up a bit, when we did these instructions, what we might want to do is, like an in A4 to read that value, and we may want to turn right around and do an out A4 to get that value back into the counter so that when we restart the counter, it'll pick up from where it left off. Okay, so we would do an in A4, out A4, and then we would, move that into the C register. and then we would do an in A5, out A5, and then we would move that into the B register. Okay, so we might want to do this. If we wanted to start counting again where it left off, we would need to take those values that we received and reload them back into those registers. Okay, so that's the final little caveat to using this timer. I think that's everything at this point. You should be able to program this timer, and anytime you want, go back and read that value. What we'll talk about next time is how to handle that timer specifically for the SBC85 if we want to use that timer in this reset 5.5. And the reason is we go back to the last video, we can't use this in the monostable mode because that pulse width is too short for the reset 5.5. We have to use this in the square wave. That means we have to treat this properly, or we could wind up getting multiple interrupts during that square wave. Okay, so we will talk about that probably in the next video. All right, well, for the time being, you can go off and enjoy your time with this timer and test your knowledge with that. All right, well, I hope you enjoyed this or got something out of this, and I appreciate you watching. If you have any comments, leave me a note below. Talk with you later. Thank you. Bye-bye.